On this page, we'll caution everybody about something specific here. Before we leave the idea of prediction, we end with the following cautionary note. We want to avoid making predictions outside the range of data. So the one we did on the previous page, there were data values. I think it was it about the age of the person and how far they can read and everything. And I think we were kind of missing a little bit of data in a certain area. Like here, for example, maybe there was no point here. So we had to figure out what the line was and yada, yada, yada. But that was in between all the data values. It wasn't bigger than the largest data value and it wasn't smaller than the smallest data value. It was somewhere in between. So they're saying, try not to use it to predict something off to the future or in the past before all the data values in the x-axis and after all the data values on the x-axis, I guess. It's only good, it only works well and can be a good prediction of what's going to happen if we have a data value we're interested in that's somewhere in between the data values we know, or the ordered pairs. Prediction for values of the explanatory variable that fall outside the range of data is called extrapolation. These predictions are unreliable because we do not know if the pattern observed in the data continues outside the range of the data. Here's an example. Crickets chirp at a fast rate when the weather is warm. The scatter plot shows data presented in a 1995 issue of Outside magazine. Chirp rate is the number of chirps in 13 seconds. The temperature is in degrees Fahrenheit. So chirp rate, how many chirps in 13 seconds? Oh my gosh, that seems very random, but okay. And then the temperature outside. All right. Da-da-da. There is, I wonder why 13 seconds. What's so significant about that? That seems so random. There is a strong relationship between chirp rate and the temperature when the chirp rate is between about 18 and 45. What form does the data have? This is hard to determine. A line appears to summarize the data well, but we also see a curvilinear form, particularly when we pay attention to the first and the last data points. So yeah, it kind of looks linear, but if you think about it, it's more curvy than a straight. It's not a straight line for sure, because it's all the data values as you go off to the right they're not really increasing at the same rate. They're kind of slowing down, it looks like, as you go off to the right. Okay, so a line wouldn't maybe fit the data the best, but it looks close to a line, I guess. It's hard to determine. A line appears to summarize the data pretty well, but we also see a curvilinear form. So it just means it's curvy, but it looks close to a line. I'm going to finish or pay close attention to the first and last data points. Both the curve and the line are good summaries of the data, but they both give similar predictions for temperature when the chirp rate is within the range of data, so somewhere between 18 and 45. But outside this range, the curve and the line give very different predictions. For example, if the crickets are chirping at a rate of 60, which is bigger than all the data points, the largest data point had a chirp rate of 45, but 60 would be much higher. The line predicts a temperature just above 95 degrees, but the curve predicts a temperature that's 85 degrees Fahrenheit. That's quite a difference. Which is a better prediction? We do not know which is better because we do not know if the form is linear or curvilinear outside the range of the data. If we use our model, the line or the curve, to make predictions outside the range of the data, this is an example of extrapolation. We see in this example that extrapolation can give unreliable results.